We are going to check out threesome today. This is a moderately challenging problem and I think it sets the roadblock for many people. It might be difficult to come up with the optimal solution if you don't have previous experience. But of course this problem is also based on previous knowledge, so if you are stuck or just interested, stay a while and I will show you what those are. Hey guys, let's look at the problem statement real quick. Given an integer array nums, return all the triplets where the indices are different and the numbers add up to exactly 0. Notice that the solution set must not contain duplicate triplets. So what does this all mean? We have a list of numbers and we have to find three numbers such as x plus y plus z where they add up to 0. And of course there can be multiple combinations of these numbers. And duplicate triplets mean that the order of the elements doesn't matter. So for example, the set of 1, 2, and 3 will be considered the same as 3, 2, and 1. Alright, let's look at the first example. -1, 0, 1, 2, -1, -4. What are we looking for here? What combinations do you see here? So there are two solutions to this. One is -1, -1, 2. The reason is -1 plus -1 plus 2 equals 0, because this will be -2 plus 2 is 0. The other solution will be -1 plus 0 plus 1, which will be also 0. Great, how did we get to this conclusion? What was the intuition when I looked for these numbers first? I made this small animation because moving 3 pointers can be extremely confusing, so it will be easier for you all to follow the thought process. So we have 3 pointers, I, j, and k, looking for all available combinations, and if the numbers add up to 0, then we can put the triplet in the result set. I started scanning the array from the beginning, first took -1, looked at the subsequent numbers, starting with 0 and then 1, then I noticed that these add up to 0, so it goes in the result set. Then started looking for new less numbers, like 2, -1, 4, and then the same thing with the second number. When I arrived at -1, 2, -1, then I saw that it was a new solution because it added up to 0, so it goes in the result set too. For this kind of traversal, we can use 3 nested loops. It's fairly easy to do. This is the idea of the algorithm where we check all the triplets, so it's a very rudimental technique. It does the job for very small arrays, but we don't get too far. When there are even hundreds of thousands of numbers, it will get very choppy. So time complexity wise, it will be big O of n cubed, because we use 3 nested loops, and space wise it will be big O of 1, because essentially we are only using 3 pointers. And just in parentheses, usually the result array is not considered in the space, so I don't really care about this. This was a very slow solution. We have to improve on this. What can we do? So basically what we did was we had to find one number and we had to find a pair of numbers from the remainder of the set that will add up to the specific number's absolute value. In this case, we took -1 as our first number, so we have to find two numbers from this set that will add up to 1. For example, 0 and 1 add up to 1, so this could be a solution. Then we go forward and we take the next number and we look for two numbers from this set that will add up to 0. For example, 1 and -1 will add up to 0. Then we go forward again, we take 1, and we need two numbers that will add up to -1 from this set. There are no more solutions here, so we can go forward. 2. We need two numbers from here that will add up to -2. This is not possible, and so on. If you're familiar with the two-sum problem, well, if you aren't, then probably pause this video and check that out on my channel. Then you know that the second part of the problem, where we had to find two numbers that will add up to the absolute value of our first number, is a fairly easy problem. And you know that that can be solved in big O of n complexity. So we could do that, and in total, then we would have big O of n squared time complexity, because we have to iterate through the whole array with not one number, and then we have to do a two-sum on the remainder of the set. But unfortunately, this will involve a space complexity of big O of n squared because we have to store two sums results somewhere. Can we get rid of the space complexity somehow? Well, yeah. What if we sorted the array? We only need the numbers anyway, and we don't care about the original indices of the elements. There is a variation of twosum called twosum2, which basically does the same thing on sorted arrays, so we can reuse that. The main part of the iteration will remain the same, we still have to iterate through the array to take the first number, but then we can use twosum2 for the remainder of the set. And essentially, we have to use 2 pointers for this. One pointer for the left element and one pointer for the right element. And we're looking for the absolute value of the first number, right? So if we know that the absolute value of this first number is smaller than the sum, then we have to move the right pointer to the left one. And if we know that it is bigger, then we have to move the left pointer one to the right. In this case, there will be no solution because there are no two numbers that will add up to 4, so we have to move forward and take the next number, which is -1, and the remainder of the set will be this. So we initialize our 2 pointers, and let's see. -1 plus 2 is exactly the absolute value of our current first number, so this is a valid solution. In this case, we have to move both pointers and check if 0 and 1 will add up to the target number. They do, so this is another valid solution. So we move the pointers again, but we see that they crossed each other, so we can stop the execution here and find a new first number. The new first number would be -1, so in this case, does it make sense to do the same thing again and potentially find the same triplet? It doesn't really make sense, so we move 2. So our next number is 0, and the remainder of the set will be 1 and 2. So we initialize our 2 pointers. These two will never add up to 0, so we move the pointer to the left. We see that they crossed each other, we stop the execution, and look for the next first number. And at this point, I have to ask a very important question. Does it make sense to take 1? Because we already know that on the right side of 1, there will only be positive numbers, and on the left side there are only negative numbers. Is it possible at all to have all the positive numbers sum up to the absolute value of this other positive number? It will never happen, so it doesn't make sense to go forward. We have another very important rule here. If the ith element of the array is greater than 0, then we don't have to do anything because it doesn't make sense. So what is the complexity going to look like for this solution? Time-wise, it will be big O of n times log n because of this sorting, plus big O of n squared. The magnitude will be big O of n squared, so overall the algorithm will run on big O of n squared time complexity. And space-wise, it's a bit tricky though because usually it will be somewhere between big O of log n and big O of n, depending on your language's sorting algorithm. Alright, let's try to implement this on Leetcode real quick. First we need to get the elements sorted, so we start with that. Then create the result list. And then we can iterate through the array, taking all the numbers that are smaller or equal than 0. So if this number is the first one, or the number and the previous number do not match, then we can do a twosum on this. So the twosum method will look like this. We need to initialize our 2 pointers, the low and the high, or the left and the right, it doesn't matter, it's up to you how you call it. We initialize the left pointer 1 to the right of the current first number, and the right pointer to the end of the array. And then we move these until they cross. And if the sum is smaller than 0, then we know that we have to move to the right with the left pointer, also by ignoring the duplicate numbers. And if the sum is greater than 0, we can just move the right pointer 1 to the left. Otherwise, we know that the sum was 0, so we can just add this triplet to the result set. And that's it. Thanks for watching. If you found this video helpful, please give a thumbs up, subscribe, or leave a comment or a suggestion. It's very much appreciated. Bye bye.